So we are going to replicate some of the stuff in these videos here. We're going to need, I think it would be good to have either the Toy Theater or the Math Learning Center, and those play with the pattern blocks. I'm going to bring both of those up right now. And they both have their pros and their cons. This one is really cute in that when you grab these, they kind of have this weird, almost realistic movement, and they push each other around and bump up to each other in interesting ways. And that's adorable, but sometimes it's annoying. So at first I really was digging this one because it was fun to play with, but then it got annoying. So I switched to this one. And in this one right here, the thing I liked about them is the way they snap together when you get them close enough. So that was just a little easier to work with. Spinning them is a little more awkward because you just have that one thing to spin them with. So again, both apps have their pros and cons. This one's my favorite lately for the reason that they snap together. And you got the share button here. So you could build something here and share it with me or somebody else, which is kind of neat. So that's a cool feature here. And we had used some Math Learning Center stuff in previous courses. All right, so, and eventually we'll need GeoGebra geometry, but that'll be in the next stage. So let's jump on into this one right here. So this one was just to play around with the idea of angle and shape. So we played around with angle last week. And one popular way to measure angles is with degrees, and there's 360 degrees in a circle or one revolution. So we're going to use that idea to find the interior angle measures for these. So an interior angle is the angle we measure as we move from one edge to an adjacent edge. So what is that measure right there? What is on this trapezoid that measure right there? And the way we're going to do that is just use the idea of 360 degrees is one revolution. So first I'm going to do it with some real toys, and then I'll show it with those virtual toys. So with the real toys, here, and am I in the right view? I think I am. So let's look at the hexagon. And so what I'm going to do is, again, I'm trying to figure out what this angle is right here, which should be the same as this angle here. This is a regular hexagon. Regular means all of the edges are the same length and all of the angles are the same measure. So this is believed to be regular. And so what you do to figure that out is you just start putting them together. And when we put shapes together like this, this is called a tessellation. And a tessellation is when you try to like tile a floor. So imagine I keep tiling these. Now, what I care about is having a common vertex here in the middle. And notice that if I start on this edge right here and I go around, I make 360 degrees to get back to that edge. So starting here, going around clockwise, that's 360 degrees. 3 of these angles make 360 degrees, so one of them should be 360 divided by 3. So let's see, what would that be? 303 goes into 36, 12 times 120. So I think that angle, based on this idea of 360 degrees, must be 120, 120, and 120 on those interior angles. And so that's the goal here, to kind of play around with the shapes and see if we can find the measures of the angles. I'm going to do one more. So with the trapezoid next. Now the trapezoid I can do a couple of different ways. I can take a few trapezoids and try to stick them together to see if I can figure out what's going on with them. Like maybe I want to focus on that vertex right there. So I get a similar one in there. And then how would I get another in there? Well, I guess it would have to go like that. So I have 3 vertices meeting right here. And those 3 angles should be the same. They're all that top wider angle there. And starting with this edge right here and going clockwise 360 degrees back to where I started, I have 1, 2, 3 equal angles in there. 360 divided by 3 means this angle right here, I believe to be 120. Another way to think about it is just taking in one I already know. So I already know those 2 angles are 120. this sits on top of it perfectly, so that angle up here must be 120. For this acute angle down here, I could make a note that 2 of those acute angles make up that 120-degree angle of that hexagon. So that means half of 120, this acute angle here should be 60 degrees. Let's see, can I find that another way? I could start sticking acute angles together. Just sticking the acute angles, all meeting in the same vertex. I think I can do this. Probably do it more symmetrically, but okay, how many of them make a perfect circle as we swing around all those acute angles? 1, 2, 3, 4, 5, 6. So if we take 360 divided by 6, that's like 36 divided by 6, which should be 6. So 360 divided by 6 should be 60. So there's usually many different ways we can kind of play with them and figure that out. And then I just want to keep track of that on paper or in my document. Let's share. So I could try to maybe copy and paste this into a Google Doc, or I could just on a piece of paper write, I have the hexagon, and then write about the angles. Each angle here is, we just discovered 120. How do I know that? Put a brief explanation about what you did to figure that out here. So for example, here I might write that I was able to put 3 of them together to form a 360-degree angle. So 360 divided by 3 means each angle is 120. So just a brief explanation about how you put them together and how you determine that. So let's do one more of those. Let's try, I think the square's pretty straightforward. And the triangle here is a nice one to get because, and again, I prefer the physical toys, but again, most of us don't have access to that. A lot of kids are getting back in the classroom, so I think there's going to be more opportunities for kids to play with physical toys again. And the interesting thing about COVID is it's a respiratory disease. It is not passed by people touching the same toys. Right? You're not going to get COVID by touching toys somebody else touched. So that's good to know in the future. Just don't breathe when you're near someone else. It's kind of scary. All right, so let's see. I think there is a reload button here for the whole screen. And the triangle is a fun one to play with, because I can kind of see that there's going to be 1, 2, 3, 4, 5, 6 of them together. To get others to fit in there, you got to click on them and then rotate them so they point in the right direction. And there is a duplicate button here. Oh no, that's a shrink button. That's not what I wanted. There was a duplicate button here somewhere. There it is. And the nice thing about that is it duplicated it and facing the right direction. So I didn't have to spin it again. So here I can see that 6 triangles each have that same vertex, right? This is an equilateral triangle. 6 of them fit in a 360-degree circle here. Right? So if we start measuring at this edge and spin around clockwise, we get back to where we started. One complete revolution is 360 degrees, and there are 1, 2, 3, 4, 5, 6 of them in there. So then we just have to check, oh, what's 360 divided by 6? Since I have my computer here, I might as well whip out a calculator. And so I get that 60-degree angle and some men's A6 gel quantum shoes. Cool. Now the interesting thing about this triangle here is basically I can use it to build a lot of other shapes. Like for example, 2 triangles here make the rhombus. So if I know the angles of these triangles, then that means I should also know the angles of the rhombus. So I could use that as my explanation for what this angle are. So this has 2 acute angles and 2 obtuse angles there. This shape, I think I put that in the mix, didn't I? Yeah, there it is. Slightly different shade here. That one right there, notice it's narrower than any of these other angles when I try to line them up there. So one idea I had when I was playing here is, what if I took two of these and I got their angles to meet up and they kind of slid into place like that? Is that new angle the triangle angle? And it looks like it is. Okay, so let's see, I think this triangle angle is 60. So two of these make 60. 60 divided by 2 is 30. So these acute angles here should be 30 degrees. All right, so that's 30. That looks like it's 30 also. What about this obtuse one? How could I figure that one out? To figure that out, I guess I can relate it to some other figures, like, let's see, it's bigger than that one. And I think we know what that angle is. This should be the same thing. So it's bigger, but by how much bigger? Is it just this pointy part bigger? Ooh, it looks like it. Let's see, let's move that up. So this activity was just about experimenting to try and put angles together and make new angles or break angles apart. So here, I know this angle right here is 120. I just calculated this angle right here is 30. So I've just made a new angle from the top of that trapezoid to the edge of this rhombus. That's what, 120 plus 30? So this should be a 150-degree angle across the top. And if I stick this, I think that lines up perfectly. Yeah, it does. So it looks like this angle right here, this obtuse angle is 150 degrees. And if I do something that doesn't make sense in my play, just let me know. And so then your task is to make a note of what the angles are. This one just has one angle all around. This one has the obtuse and acute angle. Obtuse and acute, just acute angles, a bunch of 90-degree angles, and a square. And again, to double check that, we would just make sure that 1, 2, 3, 4 of them, 4 times 90 should be 360, just to double check that. To make a note of what the angles are, and then a brief explanation of how you came to that conclusion. So that is the pattern block angles. And oh, a protractor is nice too. I didn't mention that this thing has a protractor. So that's right here. You can actually just grab the protractor and measure stuff. And that's kind of fun too. But I think it's more fun to just play with the toys. So for example, I can stick one of these in that protractor, and then I can move the protractor to try and get what the angle is, and it will tell me. And then it's just a matter of reorienting it so it sits on the protractor nice. So that's also another way you can play here. Forgot about that feature. Good thing I wrote it down. 120. So there's a couple ways you could do it. You could just say, hey, I used a protractor. But my hope was you would play around here, sticking blocks together and see what happens. That's what I would want kids to do. But is it reading a protractor an important skill? Sure, they should do that too.